In black is the ideal fluid that we already did. In blue is the viscous corrections. So now you have this blue thing. All the rest is the same. So you do the math, okay? What you get is, again, these rules, always the same. Well, not always. Sometimes they can become different. But in this case, they are the same. The additional thing that you get is that in equilibrium, pi mu nu is 0. So in equilibrium, you are isotropic. Assuming that the variations of pi mu nu are unconstrained, right? I mean, because if you force pi mu nu to take only certain values, you can get different outcomes. But if you allow pi mu nu to get all the values possible, which is the case with Israel and Stewart, and also with the theory of elasticity, you get this. Then you get, then the information current becomes this one. Do the math. And what are you going to get? Same inequalities as before, right? Plus G greater than 0. Now, G, if your system is an elastic medium, you go to Landau-Lifshitz, you read, and you discover that G is the shear modulus of the system. So, and the shear modulus by thermodynamics is required to be positive, and indeed we get it positive. And what are these? These are the speeds of propagation of elastic waves. And by the way, they're also the characteristic speeds of Israel-Stewart theory. So if you interpret this as an elastic medium, you get that elastic waves are causal, right? These are precisely the waves that you find in Landau-Lifshitz volume 7 theory of elasticity. Those are the speeds of the, yeah, exactly. Those are the speeds of the elastic waves that you get there, and you find that they must be causal. But if instead you go and look into Israel and Stewart, these are the conditions for Israel Stewart to be causal. And it is actually a general fact. Whenever you play this procedure, you're going to get some subluminality requirements for speeds. And indeed, it can be proven that at the hydrodynamic level, stability in the sense of the information current implies causality of the hydrodynamic equations. That's something that you can prove in general. It's a typo. It's a typo. Okay, yeah, it's a typo, yeah. Then one can argue with some physics like the one you said, that it should be positive, but yeah, it should be. If you just do the thing, then this is what you get. Let me just close the thing with a little application, very brief, of all of this, okay? Because this can be used to test causality, but it can also inform fluctuating hydrodynamics in a way that has already been mentioned basically by Starinets, but in a similar way. So let's say that you have the grand canonical density operator, which is this guy, okay, with all the charges and the constant. And then suppose that psi is a macroscopic state, and p hat is the projector that tells me which microscopic states realize these macroscopic states. Then the probability of being in psi in the grand canonical ensemble is the trace of the projector times the density matrix. You plug in this row. Now, projector applied to the charge gives you essentially the eigenvalue of the charge relative to the state psi, which goes out. Then the trace of P is the number of microscopic states that realize psi. So it's e to the entropy of psi. So immediately you get that the probability of being in a macroscopic state psi is e to the phi of psi. So when you go and do fluctuations near equilibrium, you can apply this little result, okay? And so you say, what is the probability of being, so if you call psi the equilibrium state, what is the probability of having this displacement away from psi divided by the probability of being in psi? You're going to get this thing, you expand it, and you get this. So the probability distribution for fluctuations can be computed using this information current. And indeed, if you have been following the papers by Nikki Mullins and some people from Urbana-Champaign, there is also George Mauricio Hippert, they have been working on constructing theories of fluctuating hydrodynamics starting from this information current. Because you know that the grand canonical probability distribution for small fluctuations around the equilibrium macroscopic state is given by this one. So you then go on and build a fluctuating generalization of hydrodynamics that makes the correct probability transitions in such a way that this probability is preserved. This can be used also to rewrite the fluctuation dissipation theorem in a self-consistent way within this framework, right? So many things are being studied right now using this language. And with this, I think I can close. Thank you. Thermodynamic qualities. Now, if I think about hydrodynamics, and in hydrodynamics, say if you go to one quarter ion viscosity, there are also thermodynamic curves that appear there. Now, here at high derivative order, so my first thought is that they cannot be constrained. You have any comment? Let me see if I understand. They appear at high derivative order. No, yeah, I understand. Like, so what makes you think that you cannot use this procedure? Yeah. 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 So I've been generalizing this method, for example, to PDNK. And indeed, when you have a derivative expansion, there is some job to do additionally. But I think that on a case-by-case basis, you can think about doing things also in that sense. Now, so yeah, I can give you this example. So I agree in general. Let me see. So basically what you are saying can be summarized with this example. So let's say that this is a collection of, so psi, and I'm also going to have first derivatives in psi. Let's do first derivative, okay? So this is going to be a quadratic form in psi and d psi, okay? And you would like this to be positive definite, but of course there is a problem, because if I stop at first order, I'm going to have the psi term. I'm going to have the psi d psi term, right? But the d psi no, because it's a higher order, right? So if I stop at first order here, I'm going to have a 0. And this matrix can never be positive definite. And this is the reason why, to make BDNK stable, you need to break the second law of thermodynamics a little bit, right, up to higher order. Because if you enforce the second law of thermodynamics for an entropy that is truncated to first order, the information current that you're going to build is never going to be time-like future directed in general. So in principle, I agree with you. But even in this case, we were able somehow to do some reverse engineering and try to figure out what is the correct value for this term, okay? But there is no systematic procedure in general. So in general, I may agree that if you have a derivative expansion, then you are always going to have some higher order terms that are needed to make the quadratic form positive, but these terms are going to be neglected at the order where you're working. So in principle, I agree with you, but I'm not sure if it is always the case that you cannot do it. So for example, like Riemann curvature terms in BRSSS. Yeah. Yeah, we can think about it. I didn't work with it yet, so you can look into it. Yes. Sorry, could you please repeat? Mm. Yeah. 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 Yeah, in general, the gradient expansion has this problem that you want to trust it only in the infrared, but stability depends heavily on the UV. So that's in general a trouble. I agree. Oh, yeah, sorry. Yeah. You are asking, a stable system is always causal. So the statement is, if a system is stable in this sense, and it's governed by some partial differential equations, and those partial differential equations obey these conditions, then those equations are necessarily causal in the linear regime. Sorry, could you please repeat? No, so, sorry. Causality is there in a very subtle way. So if you think, let me see. Where is it? All right, here. So I want phi to be maximized whatever Cauchy surface I use to compute it, right? Phi is an integral, and I want it to be maximized no matter what sigma is, right? Provided that it's space-like. So implicit in this, there is the idea that I can prepare the system as I want on Cauchy surfaces, right? And now, if it turns out that the dynamics is for some reason fundamentally a causal, you may not be allowed to prepare the system as you want along a space-like surface. There may be constraints that propagate on different points of the Cauchy surface. So by requiring phi to be maximized for every surface that is space-like with respect to the metric, I am implementing causality in this sense. Now, imagine that you believe you have some more fundamental theory whose propagation cone is larger than the light cone, right? You have built some KSS nonlinear field model which predicts that information propagates faster than light of a certain amount. Then you can still play this game, but then instead of requiring phi to be maximized on all space-like surface, you're going to require phi to be maximized on every surface that is space-like with respect to the cone induced by your theory, right? And that will automatically give something that is consistent with the notion of causality that you started with, right? So causality enters there in a subtle way. But why is causality related to stability in this way? Causality is related to stability because of another work that I made, where essentially you imagine this thought experiment. Imagine that I have a little perturbation that propagates faster than light, okay? And it's dissipated. So it starts very big, right? It oscillates big, but then due to dissipation it decays and it essentially disappears. But if it propagates faster than light, I can move to a new reference frame where the process is inverted. Okay? Now the perturbation starts small and it becomes large. Now you can actually prove mathematically that under some assumptions, if you have a system that is acausal and it is dissipative, then you can boost to a reference frame where you are unstable. So by requiring phi to be maximized for every Cauchy surface, I'm likely requiring I want to be stable in every reference frame. And so I'm automatically ruling out causality violations. This is what's happening. Yes. Oh, yeah, that follows. That follows. Yeah. How do you show it? Basically, you prove that if you have a fluctuation, the L2 norm of that fluctuation scales like the flux of E mu, right? The L2 norm of the fluctuation scales like this guy. But then since phi grows, this guy decreases. So this L2 norm of the perturbation cannot grow too much. And this automatically, you can use it to show that the imaginary part of omega cannot be positive, right? So it automatically follows. But from here, you can get more inequalities than those from the imaginary part of omega. Because, for example, if I take the ideal fluid here, where am I? Right. So if you take the ideal fluid, the imaginary part of omega tells you that the speed of sound cannot be negative. The speed of sound squared cannot be negative. But it doesn't tell you that Cp, the specific heat at constant pressure, needs to be positive. Because the degree of freedom associated to the fluctuation of Cp obeys the equation of motion just time derivative equals 0. Time derivative of the specific entropy equals 0. So the calculating the imaginary part of omega doesn't tell you that Cp needs to be positive, right? Whereas this procedure tells you. So it is true that if you are stable in this sense, then the imaginary part of omega must be non-positive, but the vice versa is not guaranteed.
May I ask one more calculation concerning the maximization of phi?
Yes.
So can you show the maximization of phi with an integral?
Yeah.
So the question.
In a second. I need the general integral. Okay, it's there.
No.
Yeah.
Previous one. Yeah. Okay, this one.
Yeah.
So you form this function. You form this functional, which is an integration of some hyperspace.
Yes.
Now, what I'm wondering whether you're saying that you maximize this, and you consider, say, any trajectory, the parameter space,
which is allowed. Yeah.
How do you choose this sigma difference?
No, you need to maximize it for every sigma, for every Cauchy surface.
So if you maximize it, I think if you maximize it for every Cauchy surface, it's a requirement. I think automatically you will get this Hilbert vector. Because if you say that it should be maximized for every sigma, that means that eventually you will have one value for any sigma, which means that the integrand is independent of divergence 3.
Yeah.
And therefore, since this is divergence 3, this is divergence 3, I think the only condition.
I remember that there were some exceptions.
Otherwise.
I understand, but I mean, usually that's true. Usually that's true, but I remember seeing some exceptions. The people that were doing chiral hydrodynamics, they got some corrections to beta nu that apparently did not matter. Probably there were some, boundary term that integrates out or something like this.
Unless you have, of course, some external fields, for instance, it's not the case. Because if you have an ablamuti mu is not 0, some external field, then okay, beta nu is no longer a hidden vector. Sorry, you may have some condition on, for instance, electric field. This is no longer constant and becomes a gradient of the electric field.
No. That is still constant.
But if you have electric field, so
I know.
If an ablamuti mu is equal, I don't know, proportional to J nu.
No. Yeah, exactly. So, yeah, okay. In that sense, yes. T mu nu is no longer the conserved tensor. You're going to get also the term with, yeah.
My impression is the condition you find, keep finding the condition that the theta is actually better at alpha is constant, is because you have required that this expression should have one maximum independent of sigma.
Yeah.
And this automatically implies that the divergence of these guys is zero.
So I agree with the implication.
There is one question.
Yeah, okay, fine. I can have a look at that exception that I saw. Usually that's true, but sometimes it can happen that for some reason, the term disappears anyway, even if beta nu is not exactly a Killing vector. Yes. Mm.
Parts which are component to the heat velocity. So my question is...
that if you include the heat or diffusion.
If you do that, do you expect that these parts orthogonal to heat velocity affect the stability of the system?
Yes, of course. So this is the little example with only pi mu nu. If you do it with the full, diffusion and so on, what you're going to get is the stability analysis made originally by Hitchcock and Lindblom when they proved causality and stability of Israel-Stewart. They already had E mu, they just didn't know that it was related to the entropy. When you read their paper, they get this magical E mu, and they said, yeah, we obtain it by trial and error, and we use it to prove stability. And then they also discovered that it was implying causality, and they didn't know what was going on. So yes, absolutely. The first paper on this, consider Israel-Stewart with all the pieces. You can also do it with arbitrary hydrodynamic frame for Israel-Stewart. And you're going to get all the conditions for causality and stability of the given theory automatically. Yeah.
So, of course, to approach this by thinking